Hello to everyone. Today we will have a seminar of the Smart Cities and Digital Ecosystems Lab. Today, Professor Mehmet Ozkaya will present on a very interesting topic called Introducing Model-Based Systems Engineering. Why do we need modeling and how easy can we define our own modeling language and its tool set. Professor Mehmet Ozkaya is currently an associate professor at the Department of Computer Engineering at Yeditepe University in Istanbul. He holds a BSc degree in Computer Engineering from Bilkent University and MSc in Computer Science from University of Essex, United Kingdom, and a PhD in Computer Science from City University of London. Professor Ozkaya's interests include software architecture, modeling languages, formal verification, and empirical software engineering. He closely works with industry and aims to provide extensible model-based and model-driven solutions to diverse problems from different industries. So I'm very excited to have him as a speaker in our series of seminars. Please welcome Professor Mehmet Ozkaya.
Okay, thank you very much. Thank you for the very nice introduction. Today I'll discuss about modeling and also meta modeling. It's going to be quite interesting seminar, I believe. So let's start with the question of what is a model. What's a model is a really important question which has already been answered by many researchers in this field. So I just listed here 4 different definitions of the question, what is a model? So if you just have a look at those well-known definitions provided by well-regarded researchers in this area, there are some concepts which are all commonly handled in different definitions. These includes the complexity, the complex problem, the abstraction, and the product. Okay, so these are very important concepts that different definition of the model shares. So if we just have a look, so abstraction, product, and complexity, the 3 important notions that contribute to the definition of models. So if we just use those 3 concepts, we could consider model or modeling is an abstraction over a product for managing complexity. So models are essentially, according to those definitions, models are essentially the abstractions over real entities. Okay, so for instance, on the left-hand side, we have a Lego that represents a model for a Ferrari. On the right-hand side, you will see the real entity. So the left-hand side is essentially the model called the abstraction over the real entity given on the right-hand side. Another example is, for instance, the Culture Center, Atatürk Culture Center in Istanbul. On the right-hand side, you will see the actual real building, while on the left-hand side, you will see the architecture of that building, the architecture drawing of that building, which is essentially considered as a model of the real entity. Also, there is a nuclear power plant on the right-hand side, and on the left-hand side, there is a model of the nuclear power plant. So it is model because it just represents a real entity from some particular aspects that we are going to discuss. So given all those, why models are important? So that's the second question that we need to answer now. It is because it provides abstractions. And without abstractions, we as humans cannot manage the complexity of the real entities. So we need to remember that human brain may process few information at a time. Okay, so abstraction is highly essential for managing the complexity of the real products, real entities. Okay, so what are the benefits of abstracting complexities? What are the benefits of specifying models of the real entities? There are actually many different benefits that needs to be considered, paid paid attention. So I have just listed here some of them that should be discussed to better understand why models are important, why modeling is important. The first is understanding complex problem solutions, separation of concerns, visualizing complex problems and their solutions, correct interpretations of decisions, and managing different stakeholders. Early analysis and detection of errors, simulation of dynamic aspects, and involvement of different stakeholders into the development lifecycle and model transformation. If you just consider each of these benefits one by one, let's have a look at understanding complex problems and solutions. Look here, there's a model on the left-hand side and there's another model on the right-hand side, and both of these models just focus on the same system structure, Java 3D API structure. They focus on the same structure, but the right-hand side is more manageable with regard to the left-hand side. Because on the right-hand side, models are just supplemented with further abstraction mechanisms defined by the language engineers. There's a language called Lepus 3, which has been just proposed by Amnon Eden and his team at the University of Essex in the beginning of 2000s. So according to this language, it is possible to just group things together in the same hierarchy and make the complex structures easy to manage via the visual abstraction elements. So it helps us better manage a complex problem. If you just focus on the left-hand side, you will not manage to understand what's going on in the structure of the system. Another important point is separation of concerns, or in other words, here I consider it as the multiple viewpoint supports. I mean, separation of concerns and multiple viewpoint support is to do with just separating different concerns from each other and dealing with each of these concerns separately. By doing so, you just make your system, make your model easy to specify, understand, change, analyze, and transform. I mean, so multiple stakeholders can also work together. If you just clutter everything together, different stakeholders may not be able to easily just work on the problem because they just focus on a particular aspect of the problem. So if you separate the concerns, the aspects from each other, this means that different people can work on the same set of problems at the same time, and also your solution become easier to understand, easier to reason about. For instance, Crashton in the 90s separates the software architecture design into 4 different viewpoints. According to their approach, the software architectures are specified in terms of logical process development and physical viewpoint, and each of these viewpoints focus on a particular aspect of the software system's development. Okay, so for instance, here everybody knows model view controller architectural style. According to the model view controller architectural style, we just specify models in terms of 3 viewpoints. We just specify the software models in terms of 3 viewpoints, which are view, controller, and model. View here represents the user interfaces of any system. On the other hand, controller here represents the business logic, the logic of the system, and the model represents the database, the data of the system that is kept by the data. Okay, so we just separate things from each other. This makes things easy to manage, easy to reason about, easy to change, easy to understand. Okay. There's another example from an embedded systems world. For instance, on here we have a deployment viewpoint model. So in this model, we just specify the physical architecture of any embedded systems in terms of the devices and their communications. And for any for the communication of any 2 devices, you could further specify in which order these devices exchange messages, or in which order the softwares inside those devices exchange messages. So this is this interaction viewpoint model, for instance, but we separate them from each other. However, they are related. They are separate but related models. Interaction viewpoint model is related to deployment viewpoint model, but they are specified with separate notation sets. So this means that there's a support for multiple viewpoints. On the other hand, for instance, for any software inside any device, you could specify the behavior of that software using state diagram, state chart diagram. So this is behavior viewpoint model. So here we have three different models. They are related to each other, but they have different notation sets because they are based on different viewpoints. So we just specify three different aspects of the same system using different notation set, but we should remember that these three models are related to each other. Okay, so the models allows us to separate things from each just allows us to separate concerns. Another important advantage of modeling is visualizing complex problems. I mean, humans process visuals 60,000 times faster than texts. So given this, we should remember that practitioners always like to just manage problems and their solutions using some graphical notation sets. So modeling enables us to support just our problem solutions with graphical things, graphical charts, graphical diagrams. So that's why they bring us another advantage here. And correct interpretation of decisions among different stakeholders. So you could just specify your system requirements in natural language without using any notation set. You could just specify your solutions, your design decisions in natural language without just following any notation set. But in modeling, there's always a definition behind a modeling language, for instance, that we are going to discuss in a while. So since there is a definition, you can just specify model in accordance with a definition, and other stakeholders will understand your model in accordance with the existing definition. So you should be able to just enable different stakeholders to communicate on the solution in a precise way. So you will understand, different stakeholders communicate in the same manner. They will not interpret decisions differently because there's a definition behind the modeling approach that you use. So both stakeholders know those definitions, so they will understand each other correctly. But if you follow natural language, for instance, you could just try to express something with the entire freedom, and another stakeholder may interpret your statements differently in a way that is not expected by you. So that's the problem, because there is no any rules and constraints to be followed. So in modeling, you could come up with such kind of notation sets supported with definitions, so it makes different stakeholders communicate in a precise manner so that they understand each other in the same way. That's very important, essentially. And early analysis and detection of errors. I mean, with modeling, you could even prove the correctness of your system. So this is called formal verification. I mean, there are languages called formal verification language, or they are sometimes called formal specification language. With those language, you can specify, let's say, the behavior of your system in a formal, using a formal notation such as process algebra. So here there's an example from the finite state process algebra. It has its own notation set. If you use the finite state process algebra to specify your model, and there's a model checker that produces a state space from your model, and then the same model checker checks every single state here and ensure that some properties such as deadlock, such as race conditions are satisfied. By doing so, the model checker essentially consider every single state that the system behavior can be in at a time and prove the correctness of the system with regard to properties of interest, such as deadlock. So that's another important advantage of modeling. If you follow the modeling approach and use some formal specification language, you may just benefit from proving the correctness of your system behaviors. Okay, so there are many formal verification languages, and finite state algebra is one of them. There is also spin, for instance, spin model checker. There is UPAL model checker. There is some FDA model checker. There are many model checkers. If you just Google, you will come up with many. And model transformation. So model transformation enables the processing of the models. I mean, models can be transformed into different aspects. Okay, for instance, you could produce software code from your model. You could just you could just transform any abstract model into another model that could be accepted by model checkers or model simulators. By doing so, you enable the analysis and simulation of models. You could just transform your model into test scenarios. You could transform your model into data interchange formats, such as automation ML, such as XML. By doing so, you make your model to be understood by some third-party tools that accepts those data interchange formats. They are all possible. Another advantage is involvement of different stakeholders into the development life cycle. So with models and modeling, you essentially let non-technical people to be involved in different stages of software development life cycle. For instance, requirement specification and analysis. So if you just follow modeling approach, if you just enable the requirements to be specified with some abstract modeling mechanisms, users, customers, even some other non-technical stakeholders could enable, could just contribute to the specification of the requirements. If you let them use some abstract modeling notation sets, they will just specify the requirements, okay? If also those stakeholders, such as users, customers, may be involved in the design. It is totally dependent on how abstract your modeling notation set is. If you just give them an abstract modeling notation set, they should be able to help you specify the design decisions as well. And also, you could use those requirements and design models to just automate the processes in the rest of the stages. You could produce codes, you could produce test scenarios. You could even take any code and to reverse engineer into model to maintain the codes. So model-driven tools comes into stage in these three different important aspects. Okay. So we discussed so far why modeling is important, why we should specify models, why we should benefit from model and modeling. So let's now just a bit focus on what a modeling is. Modeling is essentially the activity itself through which models are specified, documented, analyzed, transformed, and even versioned. So to perform modeling, to perform the modeling activity, there are different modeling approaches that we could have a look. These are natural language, box and lines, and modeling language. So natural language and box and lines are essentially the top used techniques, top used approach in industry. Today, many industries still use natural language or just draw some simple box and lines to specify the requirements, to specify the design decisions. Okay, these are also accepted as modeling approaches. Okay, but the problem with such kind of techniques are, let's firstly have a look at the advantage. The advantage is so simple that there is no learning curve. The advantage is very simple, and it's easy to write something. It's easy to draw some charts without following any notation set, without following any rules. So you could easily communicate. You could use any office editors to specify your models. But the problem is there is no precise definitions behind those approaches. So any model that you create may not be understood in the way you expect by some other stakeholders because there is no definition behind. So they may cause ambiguous models. Those techniques may cause ambiguous models. They do not support multiple viewpoints. They do not enable model analysis and model transformation. I mean, as far as I know, there is no any tool that could just process natural language requirement specification to generate code, to perform some formal verification analysis. I don't know. So there is modeling language. Besides those two approaches, there is a modeling language concept. Modeling languages are essentially supported with a definition. They are supported with a syntax and semantics definitions. They have notation sets that consist of concrete symbols. Here in this figure, you will see the modeling language starting from 1921 till 1913 or 14 or something like that, which has been created by Juha-Pekka. So modeling languages are based on some definitions. So this means that you can process any models specified with a modeling language because there's a definition behind. I mean, the computers can understand what you model if there's a definition. So modeling language, there are many modeling languages, thousands of different modeling languages, and they differ in terms of many features. Okay, so multiple viewpoints modeling, non-functional properties. Okay, some languages, for instance, enable you to specify for any system, let's say the performance requirements or security requirements. And some languages are extensible. You could just extend some language notation set for the needs of a particular domain. Some languages are architecture-centric. They follow such paradigms as component-based software engineering. Some languages provide domain-specific notation sets. For instance, some languages can only be used in particular domains such as embedded systems, real-time embedded systems. Product line engineering is another concept that are handled by some languages, and object-oriented modeling as well. So languages are useful. We need to keep in mind that languages are useful with their tool support. So they are alive with their tool support. These tool support include the model editor, code generator, model validator, model transformation tool, and formal verification tools. So for any language to be sustainable, there needs to be behind a strong tool support, essentially. We should remember this always. And language can be either general purpose or domain specific. General purpose language provide notation set for modeling any types of systems. On the other hand, domain specific language provide domain-specific notation set for the needs of a particular domain. We'll have a look at both of them. So, as I said, using existing language is only possible if strong tools exist. There are many tools, many languages available, but only just few of them survive because they have strong tools, and most of the languages just remain in the scope of researchers only. We'll have a look at such kind of language as well. And also, let me point out, practitioners may develop their own language and tools. That's very easy. There are some meta modeling technologies which has been really popular for 15 years. Okay, so there are many important meta modeling technologies through which you could just define your own language and its toolset. We'll have a look at them quickly later on. So, for instance, here there's a UML language. So we just see a model from the UML language. It's a graphical model. There's a textual model specified with another language called Write, and also AADL. For instance, AADL is a domain-specific language. So it's supported with both textual and graphical notation set. It allows you to specify the embedded real-time embedded systems architecture. Write is just general purpose language. It's a general purpose language. It enables for the formal verification of interaction protocols for any system. Okay, UML is, everybody knows, is a general purpose language for specifying software systems graphically. So let me quickly just introduce you UML. UML is essentially the top used modeling language in industry. There are many reasons behind. Firstly, it has been used for educating software engineering in almost all the universities, and there's behind OMG consortium. And so there are many different versions of the UML language proposed so far, and there's a huge tool support behind UML that makes UML really familiar for many. So there's a huge tool support that hundreds of different tools that supports UML, enables you to specify models with UML. UML is a general purpose language. It lets you specify any software system from multiple viewpoints, including, let's say, the logical viewpoints, including the behavior viewpoint, the interactions, the physical aspect of your system. So it's good actually. Okay. It also provides profiling mechanisms through which you can extend UML to some extent. Okay, but there are some problems with UML. First of all, UML is quite complex. There are too many diagrams. There are too many things to learn. There's a huge notation set. Okay, so since people do not clearly understand the notations of set of UML, the models specified with UML may cause ambiguities in many cases. So that's the problem. Okay, so also the profiling mechanisms. So while UML is essentially extensible, but the profiling mechanisms are not so effective. There are few practitioners who are easily managed to use profiling mechanism. And besides UML, there's architecture description language. There are many hundreds of different architecture description languages which have been proposed since the early 90s. So those architecture description languages, unlike UML, just focus on the software architecture. Okay, they focus on specifying the components, connectors, and configurations. So components represents the main units of the system, main computational units of the system. Connector represents how those units come together, their connections, and also the protocols of interaction. Configuration just represents the entire software architecture of any system. In the configuration, you just specify the instances of the components and connectors and compose them to create the system architecture or software architecture. There are hundreds of different architecture description languages, and some of them are general purpose languages. They enable you to specify any types of system software architectures, while some of them focus on particular domains. Okay, so if you just have a look at the diagram here, there are many general purpose architecture description languages. They are for the research purposes. Okay, those languages just propose some important notions to the research community. However, they are not used in general by the industry. So the language used by the industries are essentially those that are domain specific. For instance, AADL, we will have a look. The most popular domain specific architecture description language is for the purpose of specifying the embedded systems, real-time embedded systems architecture. So if we go further, let's have a look at a really inspiring language, architecture description language, which has been proposed in the late 90s. It's called Darwin. Darwin has been proposed by the researchers in Imperial College in United Kingdom. So Darwin just proposed the notion of dynamic software architectures. So with Darwin, the researchers just proposed the idea of specifying dynamic software architectures that change during the system execution. So the new components are created during the system execution under some conditions satisfied, or the existing components may be removed from the system architecture under some conditions satisfied. So Darwin provide both textual and graphical notation sets. And Darwin, for instance, the components are specified here. As you see here, we just specify a set of components inside another component dynamically. I'm not going to get too much into details about the Darwin notation sets. So Darwin also supports behavioral specification with process algebra. So you could specify the behavior of any of these components. With process algebra. The disadvantage, first of all, it's not used in industry. There is no inaccessible modeling toolset. I mean, as I said, these disadvantages are not because Darwin is not good. Darwin is essential and inspiring language. It's because Darwin is just for the purpose of proposing some notions, which is dynamic software architectures. That's why it's not used in industry. There is no support for the connectors, for instance. Darwin do not consider connectors as first-class citizens. Connectors are basically just the binds, which connects the interfaces of different components. On the other hand, Write is another language. Write focuses on the notion of connectors. Write consider connectors as first-class citizens. So that's why there is a connector notation sets, just like component in Write language. Write has been proposed by David Garland in Carnegie Mellon University in the late 90s or the beginning of 2000s. So Write is the first approach that proposed the notion of connectors for software architectures. Write just promotes the idea that connectors should be regarded as first-class citizens. By doing so, the components can be specified in a more reusable manner. Okay, so because connectors just encapsulates the protocols of interactions. If you do not use connectors, those protocols of interactions needs to be encapsulated inside the components. So you make the components specific to interaction protocols, so you cannot reuse them in different contexts. So Write brings the idea that, okay, let's just take the interaction protocols and encapsulate them as another notion called connector. So that's another language that's really inspiring for the entire community of software engineering research. Okay, so it just promotes the idea that, okay, connectors needs to be really important. So in the connector, there are roles. Those roles are played by the components interacting through the connectors. And there's a glue, for instance. Glue represents the interaction protocol. In other words, a global constraint on the interactions of the components playing those roles. Okay. Rapid is another language, another very early language proposed in the late 90s or the beginning of 2000. I don't really clearly remember. Rapid proposed the notion of asynchronously communicating components. So Rapid just focus on the asynchronous communication between different components using events. So that they just enable for specifying asynchronous behaviors of components, and Rapid supports a simulation of the component behaviors and their asynchronous interactions. Rapid has been developed by the Stanford University and AADL. So let's have a look at now the domain-specific language. So far, we've gone through essential general-purpose language, but that domain-specific language that just focus on the needs of a particular domain. For instance, AADL just focus on real-time embedded systems, and according to the recent surveys, AADL is essentially the top used architecture description language or modeling language. It's the top used modeling language in industry. Why it is top used? First of all, it focuses on the embedded systems architecture, so it lets you specify the architectures of embedded systems. But the main reason behind its popularity is to do with the tool support. There is a set of strong tools behind AADL. There's a set of strong tools. I just written here the names, open source tools, Osate and Compass. These tools enables practitioners to use AADL and specify the system architecture models, analyze their models for some non-functional properties as well, such as performance, security, and resource consumption. And also those tools take the model and generate code as well, a C code for embedded system devices. So for instance, here there's a notation set for AADL. So AADL enables multiple viewpoint modeling. So you could specify the software architecture using threads and processes, and you could specify the hardware architecture as well, including devices, memory, and processors. So processors run inside devices, and so on and so forth. So you could specify the system architecture using the composite notation. So AADL supported with both graphical and textual notation sets. So if you like, you could use textual notation set as well. There's another interesting modeling language which has been recently proposed. It's a recent language called Modelica. Modelica focuses on the modeling of cyber physical systems and their simulations. It's essentially considered as an open access standard proposed by the Modelica Association, including members from Europe, USA, Canada, and Asia. And the advantage of Modelica is it provides hybrid notation set, and it enables you to specify the cyber physical system models from different viewpoints, including mechanical, electrical, hydraulic control, and state machine viewpoints. Okay, it's an object-oriented modeling language, so it supports such notions as inheritance. So you could just specify any component that inherit another component. Okay, so Modelica is supported with a number of simulators. So you could use those simulators to simulate any system behavior, for instance, specified using the Modelica language. Okay, that's the basic advantage of Modelica. It's not so it has a quite complex definition, so it's not so easy to use, easy to learn and use. There's a learning curve, and also you cannot extend Modelica. You cannot extend AADL as well. These are domain-specific languages, but they are not extensible. You cannot just extend, add some new features, add some new concepts. It's impossible. And there is no any formally defined semantics behind those languages. So this could be considered by some people as disadvantage, because if there is no formally defined semantics, sometimes the meaning of the notations might not be understood clearly. This is an example of a Modelica specification. For instance, you specify a body model, and rocket model just extends the body model. So it includes all the data included inside the body. You could specify equations because here we just focus on cyber physical entities, and so on and so forth. So Koala, for instance, another domain-specific language that I quickly discuss. Koala is interesting because it proposed the notion of product line engineering, and which is highly important today. Product line in engineering enables you to consider the variabilities, okay? Variabilities while specifying the models of software systems and developing them as well. For instance, here there's a model specified with Koala, and in this model, there's a variation point here, okay? So this means that in one context, you could use in-memory data store. In another context, you could just use relational data store. So there's a variation point here. It enables you to just specify, with Koala, you could specify a families of products, okay? So far, we haven't seen any language that supports the specification of families of products, product families. So each language so far that we have seen focus on a particular product architecture, okay, or particular system model. But here you could just consider product families. So because there's the notion of product line engineering, such as variations, okay. So that's why Koala is quite interesting and also inspiring. So, having discussed different and important modeling languages, let's now have a look at another important concept called meta-modeling. So meta-modeling is really important because it needs to be understood clearly if you want to define your own language, okay? So just let's have a look at a really important diagram provided by Karagiannis in an article called Meta Modeling Platforms. So here, model is essentially an abstraction over an original entity and created with a modeling language. And there is a meta model that's an abstraction over the model. And it's essentially a model of a modeling language. So each modeling language uses essentially a meta model. It's based on a meta model. Each modeling language is based on a meta model. And meta model is created with a meta modeling language. So meta modeling technologies that I've just briefly mentioned in the beginning provides you the meta modeling language, and you use those you use the meta modeling language of the meta modeling technologies to specify the meta model. Okay, meta model is essentially the abstraction over model. It gives you the concepts and their relationships, and then you just use the meta model and come up with a modeling language. Modeling language includes the symbols. Okay, the symbols corresponding to the the concepts. Okay, so these are very important concepts that needs to be first understood. So so if you want to answer what's a meta model, okay, so that's the question. That important definitions provided, you could have a look. For instance, a meta model defines a modeling language in which a model can be expressed. A meta model is a specification model for a class of software under specification, where each software under specification is in the class is itself a valid model expressed in a certain modeling language. So you just have a look at an example. Here. There's a meta model definition here. So in the meta model, the concepts and their relationships are given. Okay. So for instance, the house language meta model, there's a house concept, and house concept is composed of 0 or more floor concepts and human concepts, and each floor is composed of 0 or more room concepts, and each room is composed of 0 or more door concepts, and they're all just inherit from the named element. So according to this meta model, you specify a model. Okay, so the concepts and the relationships needs to be followed while specifying model. So as you see in the model, there are some concrete symbols. Those symbols are essentially the language itself. So you use the language, okay? And in other words, the concrete symbols corresponding to the concepts given in the meta model, okay? And you need to follow the rules given in the meta model, the rules between the concepts relation, the rules on the concept relationships. For instance, there's a floor here. Floor modeling element includes dining room, bathroom, and some things. And here there's a relationship between dining room and bathroom with some human. Okay, so which satisfies the rules specified in the meta model. Another example is given here. There's a language definition. So there's a meta model definition. So meta model definition gives the concepts for the language. So it gives the concepts and their relationships. And the language definition gives the concrete symbols corresponding to each concepts and their relationships as well. And you use the language to specify the model in accordance with the meta model. Okay, you use the language to specify. So for instance, this is a language for specifying model view controller based software architectures. So you just specify model view controller based software architectures. So here's the language definition, and the language definition is based on meta model. Another example is a requirements modeling language for the production planning in manufacturing. So these are the languages that we developed in our research group. So in this language, there is a meta model for a particle viewpoint. So this is the process viewpoint meta model. It includes the concepts and their relationships. And here, the notation set, the language definition. It just defines the concrete symbols corresponding to the concepts given in the meta model. And using the language definition, you come up with a model. Okay. So we discussed the meta modeling. Now let's have a look at the meta modeling technologies. So if you want to define meta models and the language, you need to use meta modeling technologies. There are many meta modeling technologies. It allows you to define the meta model, which we call as abstract syntax, and also the language itself, which we call as the concrete syntax. Okay, and these meta modeling technologies let you define the meta model and the modeling language and produce an editor to you, so that you can specify models in accordance with the language and its meta model. So it produces you the modeling editor automatically. You don't have to do anything. What you are supposed to do is define the meta model and the modeling language using the meta modeling language of that technology, and the technology gives you the editor automatically. And those technologies differ in many aspects from each other. Some of them enable you to define textual language. Some of them enable you to define graphical language. Okay, some of them enable you to define semantics definition behind the language. And they provide editors with different services, including model highlighting, navigation supports, folding models, syntactic completion templates, comparing different models, and so on. And those technologies also provide you some code generator definition language. And you could use the code generator definition language to develop your own generator and integrate it into the editor. So you could enable your models to be translated into some other model, maybe some code, some other model automatically as well. So these meta modeling technologies gives you the code generator definition language through which you could just develop your own generator and integrate it into the editor of your language. So that's also possible. And validation also are enabled by some of the language. Some languages enable you to define rules, okay, for the language, validation rules, and so on and so forth. We have analyzed the existing meta modeling technologies. So there are many technologies available, essentially. That, for instance, Sirius is the top used technology in industry. It's based on Eclipse modeling framework. There is GEMS, is again based on Eclipse modeling framework. Metaedit Plus is highly popular again, which is not based on Eclipse modeling framework. It has been developed by a MetaCase company based in Finland. Xtext is again an Eclipse-based, is again a meta modeling technology based on Eclipse modeling framework. Sirius and Xtext are free of use. Metaedit Plus is not free of use. It's kind of commercial tool, but for research purposes, they provide important facilities for the users. Personally, our group mostly use Metaedit Plus for many reasons. We also use Sirius and Xtext. So Xtext, Sirius, and Metaedit Plus are essentially the three technologies that we use, but we just come up with many languages with Metaedit Plus relatively serious. So for instance, this language has been developed with Eclipse Sirius. This language has been developed with Metaedit Plus, and so on and so forth. So you could just analyze different technologies from different perspectives and choose which technology suits you best. For instance, vendor lock-in support. For instance, Metaedit Plus just enables you to export the models into XML formats. For instance, Sirius, Xtext, Graffiti, and some other languages are based on Eclipse modeling frameworks, and some languages are accessible over internet, so that you could just specify the meta models. You could just define the meta model without downloading and installing any tools. And some languages provides you the ability for model and meta model versioning. You could version the meta models, compare them each other. Some languages enable collaborative modeling. They provide you some infrastructures for collaborative modeling and even meta modeling, and so on and so forth. And there are some other requirements for which we analyze the technologies. You could have a look if you're interested. There's a paper published that includes those analysis results. So let's focus on the Metaedit Plus technology. So Metaedit Plus has been is a very mature technology. I mean, it has been developed more than 20 years ago, and is one of the top used meta modeling technologies today. It's the only thing is it's not free of use. You have to pay for that. But if you use Metaedit Plus for research purposes, not commercial, it's quite cheap. So the thing is, Metaedit Plus enables you to develop a graphical modeling language and their tool sets. So for instance, you first define the concept using the user interfaces provided by this technology. You define the concept. So in other words, the paths of your meta model. You define the concepts of your meta model. You define the relationships and the rules of those concepts. So these are the user interfaces provided by the Metaedit Plus technology. So you use those user interfaces to define your meta model. Okay, so you define the concepts, their rules and relationships. And then you define the symbols corresponding to each concept. Okay, you define the symbol for each concept, again, using the user interface provided by Metaedit Plus technology. Then Metaedit Plus provides you an environment through which you could develop your code generators. Metaedit Plus has a language called Merl, and this language is a template-based language. Using the Merl language of Metaedit Plus, you could just develop generators and integrate them into the editor. So here's just a user interface through which you could use the Merl language and develop some generator. Okay, and whenever you define your language and generators, Metaedit Plus gives you the editor automatically. It gives you the graphical editor. Using this graphical editor, you could just specify models in accordance with your language and generate code or some other things from your models in accordance with the generators integrated to the editor. Okay, so the references of the presentations are given here. That's all that I would like to discuss today, introduce today. So thanks for listening.
So thank you very much. It was very, I think, enlightening, very informative talk. I believe personally that the engineers should do more modeling instead of hacking. Unfortunately, there are, many people see computer science only as writing programs without any modeling and thinking. So I think every student must be educated in using these tools, and also provide additional tools where necessary. Researchers must be active on that. So from all these perspectives, I'm very grateful that you gave a nice summary of the possibilities right now.
Thank you very much. I hope that engineers will benefit from those concepts, and I strongly agree that modeling needs to be used in a very intensive way, so that the quality software systems can be developed in the shortest amount of time, together with different stakeholders involved in different stages of software development lifecycle.
So I wouldn't agree more than that. So of course we try to do more engineering, more science than just constructing and building code. Also, of course, defining architectures and modularization of solutions are very important. And nevertheless, because there are also many open questions, so I would like to also maybe inspire researchers within this context. So I would like to get your opinion in some of the critical topics in modeling. Although people don't use always, many programmers especially because I think they don't get the right education during university studies, too much emphasis on coding and learning language syntax. I mean, not the modeling language, but I mean the coding languages. So also there is a lack in, I think, education in doing more conceptual work. But even people are using, only programming languages without modeling and no conceptual formulation of solutions. They use many libraries. So many of the libraries, in fact, they have their embedded models in them, although they may not be presented in this way. But when you look and when you refer to a library with some interface specifications and attributes, actually, of course, in all these, there are some implicit models in these libraries. So can you say something about it, or how can we extend the trend of, let's say, using libraries to modeling?
I agree. I totally agree. The libraries are supported with some definitions that just explains how the relevant components could be used, including their interface definitions. So, I mean, the libraries are, to me, are a really important example for not only to the student, but also the industry. I mean, yes, it's an example of modeling, and to me, the industries and even the companies needs to have their own libraries for their problem domains, because I mean, the main problem in many companies is they focus on different software development projects without just creating any libraries. Actually, whenever they start on working on a different project, and they do not know actually how to reuse from the previous project. So the library concept is really a good example, and it's an approach for modeling, and I really encourage the companies to come up with libraries as well, because that's how they could reuse the solutions. I mean, the libraries are important, just consideration for reusability, and so how the libraries could be improved further is, I mean, maybe the libraries may be supported with visual notation sets as well. I mean, not only the textual but visual as well. That's what the students are always, as far as I observe, they just better focus on the visual description of the entities and the relationships. Maybe they could be supported with visual notation sets, a visual description of the components as well. But to me, the most important thing is the libraries are really important, and they enhance the reusability, as everybody knows, and the companies needs to follow the same approach and come up with their own software libraries.
Okay, so this could bring, as you said, some perspective. So in fact, many people claim that, okay, models are not that much used, but in fact, they are used in terms of libraries in the best case, maybe. So not always, unfortunately, but libraries can be very helpful, as you said. Another question I have is that the solutions and the processes that we want to deal with can be too complex. So therefore, we have these, of course, as you presented, models like UML and others, architectural description languages, but processes can be too complex and not so deterministic. So there are also efforts like based on agents and more probabilistic behavior. People are defining models, let's say, using agents and not specifying everything precisely, but more by using, let's say, statistical methods do simulations and try to analyze, complex systems. So sometimes if the problem is too complex and too stochastic in nature, we may have probably models also using these technologies. Do you have something to add on it? Because you haven't discuss these kind of models in your presentation.
Yeah, I haven't discussed. That's an important point. I mean, there are essentially some domain-specific language. As far as I know, some language that focus on stochastic models, but those languages are not so open to industries. They focus more on the researchers. They just remain in the scope of the researchers who propose ideas. But such kind of issues needs to be maybe solved in the following way. I mean, that's what we do. I mean, the problem needs to be first defined. I mean, it's the problem that could be solved could be really huge and complex. So we need to define the sub problems, the requirements of the problem, and for each requirement you may try to just propose some different languages as well. I mean, you don't need to always just solve the entire problem with a single language. You could just come up with multiple languages, or a language with multiple viewpoint supports. And so with modeling, you just essentially come up with the concepts, and those concepts let you specify what the user is expected to contribute to the model. I mean, the rest of the things can be handled by the generators. So still we could abstract many things with the models, but for the stochastic modeling, actually, I don't know any industry-based language, but we need to search for it.
So maybe agent-based languages. There are some agent-based languages where you actually the problem you analyze by, let's say, forking processes of agents, and they communicate in some random way, and then you get some behavior, emerging behavior. For example, when we work on emergency management of a large city, we would like to analyze behavior in a large city, like in Istanbul, and you cannot really precisely model it, but nevertheless you can define certain processes, and then you can just let them go, and then behavior appears, emerging behavior appears. So this was actually in my idea, but as you said, there shouldn't be one single viewpoint. So this could be one viewpoint, but for some cases, you need to have, of course, more deterministic way of modeling to at least address certain problems.
Yes, emergent behavior is really important thing. I mean, for distributed systems, I remember once that we just had a language that focused on the specifications of distributed system behaviors, but in that case, the distributed system behaviors are just specified locally. So that is, we specify the behaviors of each agent, each component in a local way. So, and the different components, different agents cannot see the state of each other. This means that we just analyze the behavior locally for the components. So we do not know what happens when those components are just executed together. Of course, there are some emergent behaviors, and this is the case, especially for the distributed systems. But if you want to control the emergent behavior, you need to specify some global constraint. In that case, whenever you specify global constraint, your system becomes centralized. It's not going to be distributed. So that's quite something that we need to discuss further. So because if you may have a distributed system and you want to control the emergent behavior, this means that you need a global constraint, and you just constrain the behavior of the entire systems interacting with each other. And in that case, your system will not be considered as decentralized system because there's a controller in the middle. For distributed systems, there's the case of emergent behaviors, and I don't know how to just control it. If you want to control it, to me, there needs to be a controller, and this makes the system centralized.
Well, okay, this is a very interesting topic. I will. So we have been, discussing for some time. So I think we should come to an end. But I have a number of points. Maybe you can just say a word. These are, very long debated issues related to modeling. Sometimes people say, okay, defining models, this is quite costly and takes time. So this is the first claim I have on my paper against modeling, although, as you know, I am in favor of modeling. The second thing is about consistency among multiple viewpoints, that it can be also an issue. So somehow you have to integrate them. Of course, we know that Crookton and some others have some proposals to integrate them, but still it may be an issue. So the second point is consistency among viewpoints. The third may be if you have a model and an implementation, you have to get them together somehow. If implementation changes for some reason independently, then model has to change, or the other way, vice versa is also true, of course. And then there has been a large debate about model-driven and data-driven approaches. They all have their advantages and disadvantages. But when we look at the developments in machine learning and big data and data analytics and so forth, so somehow we want to combine, traditional modeling with data-driven approaches, if you may call them like that. So my questions are: defining models can be costly, consistency among viewpoints, consistency between models and implementation, and combining model-driven and data-driven techniques together. So I think these are, of course, we don't have maybe explicit and concrete answers to that, but these are the discussions we frequently hear from the expert domain.
Yes, exactly. Exactly. I mean, models, yes, specified models could be costly, but if you want to develop safety critical systems such as, railway systems, defense systems, you have to model. You have to prove the correctness of your system before you implement it. Otherwise, you may end up with an unreliable solution. So there's an Ariane 5 explosion. People know Ariane 5 is because the defensive programming is not just documented. There's a lack of modeling in Ariane 5. That's why there's an explosion. So modeling is important. For instance, can you imagine that you develop let's say cruise system without modeling, and you don't and there's an issue, and you will end up with a catastrophic deadly result. If you want to just prove the correctness, you could do this with abstract modeling. You cannot just prove the correctness of any behavior by just testing it. You have to specify formal models using formal verification techniques. One of the reasons why we should model. If you work on a complete safety critical system, you have to model because you want to prove the correctness. For the consistency, consistency is provided. Yes, whenever you end up with a language with multiple viewpoints, you have to also define how those viewpoints are related to each other, and then you may easily just develop a validator and integrate it to the editor that checks whether those relationships are followed while specifying multiple viewpoint models. That's what we do in many occasions. So you could easily check the consistencies. For instance, you specify requirements model, you specify the software architectures, and whenever one of the requirements specified in the requirements model are not associated with any components of the software architecture, then there's a warning. Then there's a warning message displayed. That's perfectly possible, and it's very important. I mean, in multiple viewpoints models, you need to define the relationships, and also the tool needs to check those relationships while we are modeling accordingly. And regarding the implementation question, yes, that's correct. I mean, you specify some model, you generate code, later on you change the code, and your code becomes just inconsistent with the model. It is called architectural drift, as far as I remember, architectural erosion. If you do not want to just fall into the architectural drift or architectural erosion, you have to just come up with a reverse engineering tool as well. I mean, there needs to be a reverse engineering tool that takes the modified code and produce a model, and the model needs to be just checked whether it satisfies the properties or the design decisions. That's also possible. We experimented with such kind of a tool, developed such kind of a tool with a PhD student before. So that solution, that problem could be solved with the reverse engineering tool. So I totally agree that model-driven techniques needs to be just combined with artificial intelligence techniques. I totally agree with that. And hopefully, maybe in the future, we could together have some research on combining AI techniques with model-driven technologies, model-driven language.
Okay, thank you very much. And I just want to add my experience. I was with some construction engineers, really physical construction, building engineers. And I realized that they have now tools, and they have also multiple viewpoints. Interesting thing is that the tools really do model checking and analysis of different viewpoints in building, let's say, real buildings. And very similar techniques we used to, have in software technology. And what they told me is that in complex constructions, many on-field errors happen, and they can be very costly also. And now they really simulate a building, constructing a complex building before they start building. And the system identifies many complexities and issues, and they really try to solve these, using these tools. So, there is one saying, every company is becoming or will be a software company, or has become already software company. And I realized that construction companies are now also using very complex tools with model checking, static analysis. And in fact, they say to me, building is not an issue, but correct building and not, facing with building challenges while you are building, but at forehand, simulating them and learning from the mistakes and improving the building process. They say this is the key and the future. So now I start to believe that even construction companies are becoming software companies. Thank you very much for your presentation.
You're welcome.
This was the last in our series of presentations. It was a very valuable contribution, and I wish you the best. Thank you.
Thank you very much. My pleasure. See you soon.
Bye-bye.